Okay, in this video is another example of periodic functions. Assume that you have a periodic function just like the absolute of x, but actually repeats every 2 pi. Like this. This is copy here and then copy here and so on. So it's in Spanish will be like diente de sierra periodic function. Now, what we are going to do is to calculate the coefficients of a0, an, and bn such that the Fourier series matches the periodic function. Okay, now pay attention to this part of the plot, which is just the one that we are interested from minus pi to pi. Now, first thing here, is it an odd function or an even function, or is not neither of them? Right? Now, lucky for us, this is an even function. Okay, so let's see what happens with even functions. Okay, let's calculate the coefficients. So a0 is going to be a0 is going to be 1 over 2 pi integral from minus pi to pi of the function of the absolute value of x differential of x. Right? If we replace the value of the absolute value of x. Now, because it is an even function, we can replace this by 1 over 2 pi and then 2 times the integral from 0 to pi. Now it's the same. Because this area is the same as this area, you don't have to calculate from minus pi to pi. The only thing you have to do is from 0 to pi and then make it double. Right? And because it is on the positive side, you only need the x differential of x. So this is going to be 2 and 2 cancels, 1 over pi. The integral of x is going to be x squared over 2 from 0 to pi. So it's going to be 1 over pi, and then it's going to be pi squared over 2 minus 0 squared over 2. This is just pi squared over 2. Now, pi squared over pi is just 1, it's going to be pi over 2. Now, this is the value of a0. So, here's the objective here is just to calculate the coefficients a0, an, and bn. Alright? Okay. Now, let's calculate. I'm going to skip the calculation of an. I'm going to make bn first. Now, why I'm going to make bn first? 1 over pi, and then integral from minus pi to pi, and then the absolute value of x, and then the sign of an x differential of x. Now, what happens here is that the absolute value is an even function and the sign is an odd function. So all this is odd function. Now what happens with the integral of an odd function from minus pi to pi? Now this is equal to 0. So that is why I made it first. Okay? With practice you will notice which coefficients will be 0 and which ones will not be 0. Okay, now let's calculate the value of an. Okay, the integral, 1 over pi, using this formula, 1 over pi, integral from minus pi to pi of the absolute value of x, and then the cosine of nx differential of x. Now, here it is an even function times an even function, then the result is going to be an even function. So we can replace this using the property of 2 over pi, just the integral from 0 to pi. Because it is from 0 to pi, it's just x. X, the cosine of an x differential of x. Now, we are going to need to apply integration by parts there. So I'm going to choose u and this differential of v. So u is equal to x, so differential of u is equal to differential of x. And differential of v is the cosine of an x differential of x. So v is equal to 1 over n, the sine of an x, and that's it. So an, if we apply integration by parts, we're going to be an is going to be 2 over pi, and then u times v, x over n, the sine of an x. This is from 0 to pi. So remember, it's u times v minus the integral of b differential of u, 1 over n, the sine of nx. Differential of u is just differential of x from 0 to pi. Okay, now this is equal to 2 over pi. Now let's do the evaluation of this. Pi over n sine of n pi here. I am replacing the value of pi in the x, minus 0 over n, the sine of 0. Okay, now this is just this part now, minus this 1 over n, I can take it outside, 1 over n, integral of the sine of n, we need 1 n and then 1 over n here, so this will become 1 over n squared. Integral of the sine is the minus cosine, so this becomes positive, cosine of nx from 0 to pi. Okay, now remember the sine of n pi is always 0. 0 times the sine of 0, 0, so all this part is just 0, except this part. Okay, so n is equal to 2 over pi, and then 1 over n squared. Now, let's do the evaluation of the upper limit minus the lower limit. Cosine of n pi minus the cosine of 0, and this is going to become 2 over pi n squared. Cosine of n pi happens to be minus 1 to the power of n, and the cosine of 0, 1. So this is the an coefficient. Okay, so how is the Fourier series? The Fourier series is going to become like this. The Fourier series is just f of x equal to a0 pi over 2 plus the summation from n equal to 1 to infinite an, this number, 2 over pi n squared, and then minus 1 to the power of n, and then minus 1, and then the cosine of nx, and that's it. Now this is the Fourier series. I'm not going to do the practice of replacing the values of the n, but if you develop this Fourier series, what you are going to do is something like this. With a large number of n, you are going to do something like this. So it's going to converge to the periodic function. Now, why I'm doing like this, because I'm doing like this because in the end they are still cosine and the sine, so they are like this right now. When we are going to get something like this? When the n goes to infinite, right? By hand we cannot do that. Alright. Next video we are going to deal what to do when the functions are not between minus pi and pi. Alright? So what happens if the periodic function is in another, in a different length? It's bigger or it's going to be shorter than minus pi to pi. Okay, see you on the next video.